Okay, fine. Guys, does any one of you has problems with homeworks? Some questions? Let me give you a brief reminder that we have our homework already published, homework number 2. This homework located on our guide tribe GitHub project. So we have practice number 3 already, and we have homework number 2. So please give a try and practice with pandas, practice with data aggregation, and so on. I already told about it, but this is just a reminder that in this homework, you have expected output in the cells, and all you need is to write a piece of code that will generate expected output. So you just check what I'm expecting to see in this problem, and you need to understand how actually you can implement pandas query, which allow you to get a particular number in this case. So yes, please try it, and the deadline for this homework is 1st of June. And today we will move to another piece of practice. We will dive into simple machine learning models. For those of you who has a good understanding of statistical concepts, I think it will be an easy session. But after all, I think it will be useful for just to remind all this concept for you. So as always, let's create a new project. Open folder, guide tribe 3, and we will create new project using Visual Studio Code. Practice number 3. Guide tribe. Practice 3. Practice number 3. Okay, let's create new file with the same name. Practice 3. Practice 3. Sorry, I forgot an extension. Dot ipimb. Okay. Oh, yeah, it's practice number 4. I forgot. We already had a practice number 3 about statistical concepts, and this is practice number 4. Okay, let's. Yeah, now it's correct. Okay, let's start. And as always, in every data science project, we are starting with importing packages. No, first of all, we need to choose a kernel. It will be Python 3.11 as always. Let's start. We will definitely use pandas today. SPD. We will use NumPy, which we learned through the last session for operating with vectors, matrices, and random numbers. We will use matplotlib, pyplot as PLT, and we will use what else we need? Seaborn, yeah, definitely, as SNS. Okay. Let's wait a few seconds to import packages. And now let's dive into the practice. Today we will discuss about 2 simple machine learning models. I hope if we will have enough time. Our session is only 2 hours. So today we will start with linear regression model. I think all of you know about linear regression because it's kind of really popular, and it's not only in machine learning. Most of you will see this model during statistic course, econometric course, and in some, I don't know, newspapers, you may see that journalists made a conclusion based on linear regression model. So this model is popular, and you don't need a deep understanding of mathematics, statistics, and linear algebra to operate with linear regression. It is really intuitive, and I believe it will be easy to understand how it's works. But after all, linear regression is really important for machine learning because nowadays neural networks is really popular, and a piece of neural networks is neuron. And neuron is a linear regression. Like each neuron inside the neural network is a small linear regression. So actually, you can explain a neural network as a billions and billions of linear regressions, which is connected to each other. What does it mean? That you definitely need to understand linear regression to go further. You cannot understand how neural networks work. You cannot understand how you can like create ChatGPT without understanding how linear regression works, because each neural network has linear regression inside it. It's just many linear regressions inside neural network. Okay, so let me create a title, linear regression. Okay, first of all, let me introduce you a simple equation of linear regression. We have two variables, y and x. And linear regression, you have coefficient. Also, this coefficient called a slope. Slope multiplied by x plus intercept. By the way, please use this kind of equations. You see this dollar sign. If you type like this, and then you create a markdown cell in your Jupyter notebook, you see markdown. You can write an equations. You see how I do it. Right now it is equation, and in the same manner it is used in scientific publication. So each time you will use this syntaxes to create and write some equation inside your Jupyter notebooks or inside your publications. This is kind of useful because right now this equation look pretty good. Also, sometimes you see I write slope and I write intercept. In literature, it might be confusing because there are many different names for these variables. Let me show you. Sometimes slope is also called alpha. Alpha. Sometimes it's also called weight, W, this W. And sometimes it's also called beta. This is all the synonyms. So in some publications, you may see slope. In some publications, you may see alpha. In some publications, you may see weight or W, also weight. And all these 5 different words is the same. This is synonyms. So please don't be confused with it. Just different scientists, different researchers use different notation for the same concept. This coefficient in front of x variable. And also intercept, you see, sometimes it also has many different names. And one of them is bias. And also another is weight. So this is weight number 1. Sorry, and this is weight number 2. This is just a synonyms. Don't be confused. Okay, I forgot to write this dollar sign right here. Dollar sign, dollar sign, dollar sign, dollar sign. Okay, you see, right now it looks better. And also you see that using this LaTeX notation, it is called LaTeX notation, you can write Greek, Latin, and symbols from other languages. So right now I used Greek symbols. Okay, in this lecture, I will call this coefficient slope and intercept. And this kind of equation is linear regression with one variable. By the way, sometimes, let me introduce one more name. This is y is called y. Y is dependent variable. Dependent variable, or it's sometimes it also called target. This is also the synonyms. And about x variable, x variable is independent variable, and sometimes it's also called features. And also, please don't be confused with it. I may use these terms interchangeably, but you should remember that this is the same. Okay, this is just a brief introduction about notation, which took 5 minutes. Let's dive into the practice. First of all, let us understand what actually this slope and this intercept is. For this purpose, I will use NumPy, linspace from minus 20 to 20, and it will be 100 points. Let me say that x is equal to 100 points starting from -20 to +20. I will just generate 100 points, which is on the same distance to each other. And let's generate y, which will be equal to x. Y variable, y variable equal to x. We generated two pieces of data. Let's actually plot them. We will use scatter plot today. X and y, plt.plot, plt.plot, x, y, and plt.show. Also, we will use title, plt.title. This is x equal to y. By the way, when you are using matplotlib, you also may use $sign to use a LaTeX notation instead of simple like strings. Let us see what we get. Yeah, we get a simple line. This is x equal y. This is the simplest example. By the way, let me comment this. This is just a line. And what does it mean x equal y? That if you take x equal 5, y is also equal 5. This is really simple. If you take x equal 10, y is also equal to 10. By the way, let me introduce one more important thing, that instead of writing grid here, like I did during the previous session, you may fix this parameter in a very first cell. Set style white grid. Right now I use Seaborn style, and this Seaborn style used in a very first cell will be applied to the all plots inside my Jupyter notebook. Let me demonstrate what it happened. Yeah, right now I added a grid to all my plots without explicitly writing it here. I just will economy some time on it. Okay, you see how this plot looks like. Let me also add additional lines. V line equal to 0, ix h line equal to 0. And let me set color. It will be just easier for us to understand what's happening with slope and intercept if we'll have color black. I want black. Okay. Yeah, I just write it 0, x equals 0 and y equals 0 on our plot. Okay, this is a case when x equal y. What does it mean in our notation? That in this case, slope, this slope coefficient was equal to 1, and intercept coefficient was equal to 0. X equal y. Imagine that I want to plot something and add intercept. Let me demonstrate you. For instance, intercept equal to 10, and I want to create y1 x plus intercept. So, and also I will add this line on our plot. Label equal x equal y equal x plus intercept. Right here, I will use f-string syntaxes that I can put a variable inside a string directly. And also plt.legend. And for the very first line, I will use a label equal y equal x. Yeah, let's see. Oh, I got an error. I forgot to execute the very first cell. Yeah, right now we see an effect of intercept. Adding 10 to our intercept, we just shifted our line 10 points upper. In the same manner, I can create a new variable. By the way, let me do like this. Let's create y equal 2. And for y equal 2, we will create intercept equal -10. Just for the sake of visual understanding on what is going on. Intercept 2, and in the same manner, I will copy the cell and add intercept 2 to our plot. Intercept 2. what will happen? Yeah, you see, I added another line, and right now it is shifted to -10. Let me correct this. -10. Yeah, I think it's very understandable that this intercept allows us to understand at which point our line will be intercepted with line x equal to 0. So this is black line, and if I am changing intercept, this 10, I changing the point at which our line will be crossed with x equals 0. And if I change it to -20, it will be just at -20, this line. So you get what is intercept. This is a very first part, intercept. Intercept. Yeah, okay. Next, it is important to understand what is the slope and how it affects our plots. We will move in the same manner, but a little bit faster. What is slope? In this equation, let me copy paste this piece of code and just a little bit adjusting it. In this case, I won't use intercept. I will use slope, and instead of adding it, I need to multiply it. X multiplied by slope and x multiplied by slope 2. Yeah, okay. And let me change also this piece of code to demonstrate you how visually you can see different slopes on your visualization. Yeah, you see that slope, if I have slope 10, no, 10 is too big. Let's use slope 2 and slope, for instance, 4. Yeah, let's do like this. It will be better. We have our initial line, y equal x. You see how it looks like. It is blue one. And when I am increasing a slope, the angle between our line, this blue line was initial one, and slope was equal to 1. Then I changed a slope to 2. I increased it 2 times. And also you see the angle between our line y equals 0, this black one, and between our orange line, which has slope equal to 2, it's increased 2 times. Another case, when I has this slope equal to 4, already our slope from the initial line increased 4 times. And the angle between our green line and the black one is 4 times bigger than for the blue line and black one at the first case. Now you understand what is the slope. And this is essential concepts to understand a linear regression with one parameter. Okay, now we know what is the slope. We know what is the intercept. Let's directly apply it to linear regression with one parameter. Linear regression with one parameter. Okay, today, by the way, today we will add one more package to our arsenal. Today we will use package called sklearn. Sklearn datasets. From sklearn is one of the most important packages after pandas. Pandas is the most important. sklearn, I would say, second place in the work of data scientists. And sklearn is a package. Inside it, you can find different machine learning models already implemented. So like always in data science, you do not need to implement everything from scratch. You do not need to write a lot of code. You just take what is already implemented. And if you need some machine learning models, maybe linear regression, decision tree, gradient boosting, even neural networks, you just import sklearn, and you can write like import neural network from sklearn, import linear regression from sklearn. But at the first place, we won't take an implementation of linear regression from sklearn. We will try to do it by ourselves from scratch. From sklearn, import datasets. Yeah, you see, I have this error that I have not imported sklearn. Let me find how to install it. How to install sklearn. Yeah, pip install scikit-learn. You see, this name is a bit different from the name which we are using inside Python. sometimes it's happened. It's just because somebody already wrote a package which is called sklearn. And the guys who developing this scikit-learn package for machine learning need to change their naming. You can definitely go through this documentation. It's extremely interesting about sklearn. But today we will use just several functions from it. Yeah, guys, I can copy paste this link if somebody is following me during my presentation. How to do it? How to use chat? Back to meeting. Sorry. How to use chat? Yeah, I see. I found it. Everyone in the meeting. Yeah. So I will copy paste this command for myself. Pip3, and I'm using pip3. Pip3 is just another version of pip, this package manager for Python. We will wait several seconds for this package to install. Yeah, right now it's installed, and I can definitely import it. Yeah. Right now, today during the session we will use this module datasets. Datasets allows us to produce a toy data. Like you don't need a big data like 500 different rows, like 5,100 of rows. You just need to create 20 rows of data, and you don't need where to find. You don't know where to find it. For this purpose, you can use datasets, and inside datasets you have many different methods which allows you to produce a toy dataset for your particular case. Since today we are talking about regression, we will use this make regression method. Make regression method takes several parameters. One more time, this is a method for creating a toy example of data science problem. Not real problem, but toy. And this method takes several parameters. First one, a number of samples. This method asking you how many samples you want to see in your toy dataset. Let's take 15, not a lot of them. Number of features. You see here it is written features. But from the very beginning of our lecture, you know that features is the same as x, is the same as dependent variable. So right now we are speaking about linear regression with one parameter. So number of features equal to 1. And one more parameter, which is important here, is noise. I will show you what does noise actually mean, but from the statistical point of view, this is just a standard deviation of our data. On the previous lectures, I explained you that the bigger standard deviation, the more our points is spreaded around, that our distribution become wider and wider if standard deviation is bigger. And in this case, noise is the same as standard deviation. So if we have a big noise, our distribution is big. If we have small noise, our distribution is small. So let's pick up noise equal to 5. And to use this method, we need to unpack it. Okay, let's see what right now we have inside this x and y variables. X is a vector. Yeah, you see, this is 15 samples of data, and this data is applicable for regression problem. Let's have a look on y variable. This is our target. So the goal of this particular small part of our lesson is using independent variable x or feature x. We need to predict what is y. So using x, we need to predict y. And to make it simpler for us to work with it, let's put these vectors inside pandas data frame. It's just for simplicity. It's not obligatory to do. To create a data frame from scratch, we will use pd data frame method, and we will pass a dictionary inside it. So x is equal to x. Yeah, x is equal to x. Sorry. And y is equal to y. And also, yeah, I forgot to close it. And one more method which we will use here is ravel. You see, this, if you like make a look at our x and y, you see that they look a bit different. If you will have a look at shape of x, it has 1 column and 15 rows. And if you will have a look at shape of y, it has no columns. Like x right now is a column and y is a row. And to put both these vectors inside our data frame, we need to flatten x to make a row from it. So for this purpose, we will use Ravel. Okay, let's create a data frame. Let's have a look at our data frame after creation. Yeah, you see that right now it is almost looks like our data sets from previous lessons. But right now we don't have a special names for our factors. You just have x and y, and you don't actually know what does it mean. Let's plot our variables one with another. plt dot scatter x y plt dot show, and also for the sake of accuracy, plt x label. On x we have x actually, and this is feature, and on y we have y, which is a target. Let's have a look. Yeah, we just has these points, which is spreaded somehow in a space. And using x, we need to predict y. Okay, right now, we already know how to create a line using Python. That you can use these commands, and you can generate some lines with some slope and some intercept. So the goal of linear regression is to build some line which will fit the best to your data. So for the very first approach, like a baseline, let's create a random line. We don't know what is the best parameters right here. Let's just put some random line and let's see, is it good in description of our data. Okay, let's create it. X values for this purpose, np.linspace from x minimum and x maximum. And okay, let me explain what is happening here. Right now, I'm using linear space, NumPy linear space. I took the least value of x, which is something like -3, and I took the biggest value of x, which is something like 2.2. And I generate 100 points in this range. So I splitted this range from the very least value to the biggest value in 100 points. This is x value. Let's have a look at this. I'm not sure. Yeah, it's something like 100. You see x minimum is -2.45 and x maximum 1.8. Okay, and right now let's create our linear equation. X values equal to slope multiplied by x values plus intercept. Let's make some additional variables for intercept and slope. So what is the slope for this purpose? Let's say slope equal to 25. It's just random number. I don't know what is exactly solution. And intercept equal to 5. Okay, let's do it. And now let me copy paste this piece of code, and we add one more line to plot our new linear regression model. We will plot x values, x value with y value. Okay, let me call it value for consistency. Value. Okay, you see, I just took this 25 from the top of my head, just random number, and this intercept equal to 5. Also, just I picked random numbers and I plotted it. You see this line, and already it is not like it's not so bad. I just randomly pick number, and this line is actually okay. But right now we don't know, is it a line a perfect solution for our particular problem? Let me explain why it is so. For this purpose, let me merge the cells. Imagine that instead of 25 and 5, I will use 44 and 15. I just change values of slope and intercept. Let's have a look at our plot. You see, this line is already a little bit different. Okay, right now, to understand these concepts, let me create a function which will take two parameters. It will take slope and intercept, and then we will try to demonstrate different possible solutions for these problems. Okay, def plot line. This function will take two parameters, slope, and slope is float number. This is decimal number. And another parameter is intercept. This is also float number. What does this function do? It's, first of all, create this y value based on slope and intercept, and then it take this line, just plot. And also in this function, we will add label, label, and here we will pass f string slope and intercept. Don't worry if you don't understand what's happening right here. It will be clear in a few seconds. Right now, I will copy paste this piece of code, and instead of this plc.scatter, I will use plot line with parameters slope 25, slope equal to 25, and intercept equal to 5. Okay, let's have a look. Oh, something goes wrong. Yeah, I copied the wrong piece of code. We use plc.scatter. Yeah. Okay. Here, let me also label equal to data points. And what else we need? We also need to plot legend to make it clear. And one more trick, we will add color here. Color equal to color. And we will pass color to our function as a parameter. And this color by default will be none. So what does it mean? That if we don't pass a particular color, our line will be default. It will be blue. But if we pass color to our function, it will just change its color. Okay, let me plot first line with slope 25 and intercept equal 5 and color equal to red. Let's see. Yeah, our function is working. And you see we have a legend that this line, red one, has equation 25 multiplied x plus 5. Okay, let me copy paste this line, and instead of slope 25, I will use slope, 55, and intercept equal to 25, and color equal to green. And let me add one more line, slope equal to, 10, and intercept equal to 0. Okay, no problem. And yeah, I need to change color to make it better. Yeah, you see, right now, I created 3 different possible lines which might describe our data. But right now, we need to make a decision. Is any of these lines is a good solution for our problem? Because there is an infinite number of possibilities. You can pick whatever number you want for this slope and this intercept. But right now, you cannot make a conclusion. Is this line good enough or is it bad? So you need to introduce some metrics to measure which values of slope and which values of intercept allows you to describe your data in the best possible way. Using this function, I hope you understand that number of solution is infinite. You just can generate any line, even a crazy one. Let me add some crazy line. Color equal to blue and slope is minus 50. Okay, let's see. Okay, we generated this blue line, and right now, like just from the intuitive point of view, we know that this line is total rubbish. It's not a good solution. But right now, we don't have a mathematical representation. We don't know how to solve it mathematically. For this purpose, let's introduce metrics. Metrics is just one number. So out of all this stuff, we will generate one number, which will demonstrate is the solution good or bad. Metrics. This is the next part of our talk. Guys, right now we discussed pretty simple topics. If you have any questions, please ask. We will move to metrics. Okay, guys. You need one number. And in majority of cases, when you are dealing with linear regression, this number called mean squared error, MSE, or equal mean squared error. To calculate MSE, let me show you a formula. I will also use LaTeX syntax for this purpose. You need, what do you need to do? First of all, you need to take real values. This is y. You need to subtract your predicted values. Will it work? Oh, I need to create markdown cell. Yeah. You need to subtract predicted values. You need to take to square this term, and then you need to divide it by the number of samples in your observations. Sum here, and yeah, MSE equal to this one. Yeah, this is a formula to mean squared error. You predict values is this y hat is the values which is predicted by your line. Y is real values. These data points, you see, these data points is a blue points, and n is a number of the samples. In this case, number of samples equal to 15. Yeah, we have 15 samples. So let's actually calculate MSE for the case of one of this line. Let's actually introduce this MSE. Def MSE. What does it take as a parameter? It is take y true. This is a real data points, this y, and y pred, predicted values. And it's return just one number called MSE value. How to calculate this MSE value? Let me show you. Y true. This is actually really good about Python, that you almost like speaking in English. You just don't need to understand big formulas. You just speaking in English, and you are telling Python what to do. Y true minus y pred. This is y hat in our formula. We need to take np dot. No. We need to take its square. To square a number, you just need to multiply it by itself. And then you just divide it by n. And this summation in front of the formula, you just use np.sum. np.sum. Okay, is it correct? Python is writing that something is wrong here. Okay, let's see. Let's try to test our function right now. Will it give us some good results? So to test it, we need to try predict some values using this line. How to do it? Let me pick some line with I don't know. Okay, y values equal to slope intercept, and right now x value is some numbers which we just generated from the range from minimum to maximum. But if we subtract this x value with real x, these 15 numbers which we generated at the very first step, we will produce y predicted, y pred, this y hat in our formula. Let me change it, x, and it will be y pred. By the way, let me use small values here because this is convenient. Y pred, y true. Okay. Let's calculate y predicted. Yeah, we generated 15 numbers. And then let's try to apply our MSE function to two vectors. We have true values. Let me demonstrate you. We have these values from our slope line, our line, and we have our true values. It's just y. You see, this vector and this vector. And right now, we will apply this mean squared error to compare these two vectors. We have vector 1 of 15 numbers and vector 2 of predicted numbers. And we will try to compare, is second vector produced by our linear regression is a good solution for this particular problem. Okay. And for these purposes, we'll wrote this MSE function. Let's try to use it. MSE. I expect right now to see some error. And next I will explain you why it is so. Yeah, name n is not defined. Yeah, we forgot to implement n. N in this formula is a number of observation. So you can do like this, length of y true. And for our particular case, it will return 15 because we have 15 points, just 15 points in our data. Let's see if I fixed this MSE. Yeah, right now I fixed the solution. And you see it returned me one number, 60,000. Oh yeah, 60,000. So mean square error of our regression line is 1600 right now. So you see, this is an idea of metrics. You may find many different metrics. In a machine learning, I would say 100 metrics for sure. You may find 100 different metrics. But the idea is that you take two vectors, and these two vectors, you compare them and return one number. How good is your predicted vector compared to the real one? And this number is 1600. Okay, right now we understand what is MSE. And now let's a little bit change a code which we wrote previously. Let me copy paste it. I will put it here. And right now we just add a little parameter that we will display MSE on our plot. We will just check what is a mean squared error for each of the line on this out of these 4 lines. Okay, for this purpose, I copy pasted this function, and let me add MSE in our legend. I will add it here. Sorry, MSE equal to MSI y and y predicted. And also we need to calculate y predicted here. We'll slope multiply by x plus intercept. Okay, will it work? Okay, yeah, right now it's work, but it's not look really pretty because we have too many decimal places right now. Let me also add this float number rounding. Let's use 0 decimal places because we don't care about them. Okay. Oh, no, it's not really good. Let's use 1 decimal place. Fuck, sorry. Dot F, 1F. Yeah, 0F. Okay, yeah, right now it is already better. You see, for each line, instead of just looking at them by our own eyes, we introduced a matrix. A matrix is a measure of how good is our line for this particular problem. And the lower the value of the matrix, the better is our line for this problem. And right now, you see that with respect to this MSE matrix, the best line actually is not red one, is not a green one, but this with error 19,321. Yeah, the lower this mean squared error, the lower the error, the better is our line. And you see that error for green line is 87,000. The error for green line is 30,000. The error for this I don't know how to call this color, but I hope you know. The error for this line with a slope of 10 and intercept of 0 is 19,000. So right now you see that by our own eyes, we may conclude in a not in the right way. Like we can choose the line which is not actually the best solution. But when we are using metrics, we already has a good mathematical proof that one line is better than another. Okay, right now we see that we can compare different solutions and we can choose best solution out of existing ones. But then we come to the thought, actually, and how we can choose the solution which actually is the best. So we generated just some solution, but we need to find the best one. We need to find such slope and such intercept which will lead us to the least possible error. And the number of possible solutions is infinite. So it is not possible to check each of them, compare each of them, and find the one with the lowest error. So right now we are moving to the third point of linear regression, how to find best solution. How to find best solution. By the solution, I mean to find best slope and best intercept. This is next point of our today's talk. And here you can, once again, you have different possibilities. Let me show you first possibility. First possibility, you just pick up a straightforward mathematical formula, and this formula allows you to calculate best value for slope and best value for intercept. I don't remember it by heart. I will just copy paste it. I have it. I saved it in this document. And right now I will demonstrate you how it looks like. This will be scalar formula. Scalar formula. Sorry. And I will paste a formula right here. Yeah. You may calculate this coefficient. This is slope. Sorry, slope. Sorry, yeah. You may calculate slope and you may calculate intercept using this formula. Right now, it's look a bit not really good. Like it's look too complicated. But I will show you that in Python, you can implement such formula in a very simple way. First of all, let me remind you what is x and y in our case. Let me print x, print x, and print y. Yeah, x and y is two vectors. X is vector of 15 values, and y is also vector of 15 values. This is okay. Right now, let's implement this formula. Let me write it. Slope equal to. You need n. N is a number of observation. We already have n in our calculation, I hope. No, we don't have. N is a number of observation. We have 15 observation, and to calculate n, we will use len, method len. Length of vector x, and it will return 15, I hope. Let me check. Let's see, n, yeah, n equal 15 points. Let me delete this piece of code to implement this formula. Slope equal to n multiplied this summation mark. If you see this summation in some publication, in some instruction, you just need to write np.sum. This is a summation. Inside the summation, we have multiplication of vector x and y. X multiplied by y. Okay. Then, once again, minus summation np.sum. Pretty straightforward. Minus np.sum x multiplied once again by summation of y. np.sum of y. Okay, we almost completed with the upper part of our equation. Just let's use parentheses. Then let's implement denominator. We have n multiplied by summation mark. We write np.sum. X squared, x multiplied by x squared, minus, what do we have here? np.sum of x, and right now it is squared. So np.sum x multiplied by np.sum x. Okay, I think this is almost all. We write it. We rewrite this formula from the textbook. This is a formula which you can see in each textbook about linear regression. But right now we do it in practice and we implement it in Python in a pretty simple way. You understand that if you see summation, you use np.sum. If you see x, you write x. You see y, you write y. Pretty simple. And next we need intercept. Intercept. Once again, what we have here, np.sum of y, np.sum of y, minus coefficient. In this case, let me change it to slope. As I told you, this is synonyms. Slope, coefficient, weight, this is all the same stuff. np.sum y minus slope, and slope we calculated in the first formula, multiplied by np.sum x, and then we need divided by the number of observation. Number of observation in our case equal to 2n. Yeah, okay. Let's print out our slope and intercept just to check is it calculated correctly. Intercept. No, it's not looks correctly right now. Sorry for this. I made a mistake. Okay, let's check. Let's check how it will looks like. Intercept is negative. Slope is equal to 1. Something goes wrong. I don't actually see what I messed up in this formula. And p.x and p.sum x. I just see that these values, which we got right now, is not coincide with values which we see previously. Previously, we plotted some lines which not the best solution, but at least something. And right now, using this formula, I got a totally wrong solution for some reason. Let me see if I can correct this formula right now. If I don't, I will need to check my implementation from my preparation. I don't see an error. Oh, how it is possible? Let me see x. Maybe we do like this. X equal x ravel. Oh, yeah. You see, I made a mistake during my formula. And once again, I knew I need to use this method ravel. Why it is so? Because our initial x, looks like a column. When I generated it at the first place, let me see where I generated it. I generated it right here. Yeah. If I will have a look here, x is a column. It's not a vector. And to make it a vector, you need to use ravel. Sometimes it is make your solution look weird. You see, it was a column, and now I flatten it. It was a column, I flatten it. And that's why my solution was a little bit mistaken when I implemented this direct formula. By the way, let me restart my notebook because I forgotten what is the execution like linearity of my solution. Let's wait a little bit. By the way, this is a really good practice. When you are implementing some code, you're writing some complicated script, sometimes you need to restart your notebook. First of all, you will clean your random access memory of your computer from unnecessary variables. If you have big data set, it may slow down your calculations. And second, you may check if your notebook is linearly executable. So each of the cell can be executed after the previous one. Okay, I re-executed my notebook. I checked the formula. Where it is. Okay, something is wrong right now. Yeah, I see what is wrong right now. Because when I restarted my notebook, I received different random points. By the way, you see this effect that in the very first line, when we generated these random points, I didn't fix random state. So each time I restart my notebook, I receive different values of x and y. But actually, it's not a big deal right now, but you need to keep in mind. And each value in my notebook is right now recalculated, and I have different values of MSE. I have different points. I have different everything. And now I have different values of slope and intercept. Okay, it's not a big deal. Let me plot this line on our solution. Okay, PLT. I will copy paste this piece of code, and instead of all this solution, I will use slope equal to slope, which we calculated, in intercept equal to intercept. Let's see. Yeah, you see this line right now represent a solution obtained from the exact formula. So we took this formula, we implemented it using Python, we plugged in our values of x and y, and we plotted this line on our real data points. And right now, you see, actually, this solution is pretty well. That right now, these points generated, these generated points is in a good agreement with linear regression line obtained by us. By the way, you see that right now slope is 82 and many decimal places. Maybe I need to fix it. And intercept is minus 0.85. Okay, we generated this line using exact formula. We have another approach to find these values of slope and intercept. This is approach of matrix. How do you call it? Okay, linear algebra approach. Why actually we can't stop right here and we can't use this solution? This solution is the best possible solution for this line. Let me demonstrate you. If I plot another line, this one, mean squared error of our red line is 29. It is really low. And mean squared error of green line is 911. So right now, this red line is actually the best solution for the problem, best linear regression line we can obtain. But the problem of this approach of using this formula, that this formula become extremely complicated when we are doing not one variable linear regression, but two variable linear regression or three. It is not applicable when we have dimensions bigger than one variable regression. Right now, we can use it. But if you have 2 or 3x variable or even 100x variable, it is not applicable. And here we can use a linear algebra approach. To use linear algebra approach, let me find this formula. I will demonstrate you how you can implement it. Where is my notes? Oh, okay. You can implement find intercept and slope using this formula. Equal to x transposed multiplied by x, all this in a inversed matrix. This is multiplied by x transposed, and this is multiplied by y. Once again, I am using LaTeX syntaxes. You see this formula. W equal to tra-ta-ta-ta-ta. Don't worry. It's not a big deal to implement this in Python. Even though you don't understand what is the matrix how to transpose matrix. You don't understand what is the this -1. This is not the same as 1 divided by something. This is matrix inversion. This is a bit more complicated. Don't worry. We will implement it in Python, and even if you don't understand it deeply, it's okay. The question here is, what is W? And W is just a vector. Let me demonstrate you. W is just a vector which contains two numbers. It is intercept and slope. Yeah, it's simple as this. So instead of calculating intercept and slope as a two scalar values independently, right now, using this matrix formula, we can calculate a vector which will contain slope and intercept, two values. Okay, let's try to implement this using Python. We writing W equal to x. To transpose x right now is, x right, I use code. Yeah. Once again, X is a vector. We need to transpose X. We need to matrix multiplication. You need this, I don't know how to call it in English, собака, dog sign. You need this dog sign. You multiply it by X, and then you need to do this -1. Once again, it's not the same as 1 divided by this stuff. This is a matrix inversion. And for this purpose, you need to call np.linalg dot inversion. This is the same as this bracket equation in -1 power, np-linalg inversion. Then you multiplied this by xt. You see transposition of matrix dot t. And then you multiply it by y. Yeah, I forgot one more thing. Right now it won't work. I also need to make a matrix from my x. X right now is a vector, and I need to add to make it two-dimensional. np vstack np.once len x. Will it work? I hope so. This is X before I transform it into the matrix. And after I transform it, it will, yeah, T. It will look like this. I just added one more column to our X vector. This is our X values, just some random numbers, and I am added ones. I am added column with ones. Why it is so? Because when we are dealing with matrix multiplication, transformation, inversion, and so on, we need to keep in mind dimensionality. And if dimensionality of X will be not 2 by 15, it won't work. We added column for intercept, and column for intercept is constant 1. And this column, second column, is for the slope. So we, how to say, artificially added column with ones to our x vector, and we created matrix of x. Let me write it. X right now is xmat. I will call it x matrix. Okay, we created matrix of x, and let's see if we get some solution. No, it is error. Yeah, because I need to use x matrix. X matrix. Oh, it's too complicated for me. Yeah, you see, we got right now we got this vector w. Let me store this variable in vector w. We got this vector w. Let's see, and it has two values. It has 82 and it has minus 0.8. So this is a slope and intercept. On the second position we have a slope, and on the first position we have intercept. This is a second approach how you can calculate a good line for your linear regression. Let me copy paste our piece of code, and instead of slope, I will use w0. Yeah, w0 I am using as intercept this value on position 0, and as a slope I am using first value. Okay, let's see if it works. Yeah, it works. And right now we have even lower mean squared error of, or not lower, I forgot it. Yeah, it's the same. Yeah, it should be the same. Okay. You see, using two different approaches, using this direct formula, which we implemented in Python, we got coefficient 82.62 and so on. And using this matrix approach, with matrix multiplication, summation, and so on, we got the same values. So this is just two different approaches when you can get the same good solution, not good, best solution for your linear regression. Okay, this was one-dimensional linear regression when you have only one descriptor x. Let's move to two-dimensional linear regression, and let's see how it actually looks like. For this purpose, let me create a new title. By the way, we need to stop in 40 minutes. Yeah, in 40 minutes. Okay, I will briefly explain you two-dimensional linear regression, and then we will do linear regression with real problem. And right now, let me write two-dimensional linear regression. Okay, two-dimensional linear regression. Let's have a 5 minutes break. 5 minutes break. I will get a cup of tea. We will do two-dimensional linear regression, and then we will solve real data science problem using linear regression. I think in 1 hour we will finish. Okay, guys, keep pushing. I hope you are still with me. Let's have a 5 minutes break. Okay. We have only 25 minutes till the end of the session. Okay, we have not enough time for discussing two-dimensional linear regression. Let's move into the practical, real problem solving with regression. Okay, to solve a real problem, first of all, we need data set. How to find data set when you have no CSV file? For this purpose, we will use datasets. Datasets is a part of sklearn library, which we imported in the very beginning. And here you can see many different methods. Let me pick some data. House, California housing, and df equal no x. No, not California house. Diabetes, breast cancer, sample image, wine, iris. Iris? No, not iris. I'm just choosing which data set is best here. Okay, let's download some data set from Kaggle. Let's do it quickly. Kaggle. Data set. What we need is regression. House prices. Yeah, house prices. House prices is kind of good data set. I will download it. Let me share a link. Tick. Back to meeting. House prices. Description. Is this data is good for us? Train CSV. Okay, let's download it. Train CSV, and I put this train CSV inside our practice folder. Yeah. Okay, right now we have a data file. And to read it, we will use pandas. pd read CSV. How does this file called? I forgot already. It's called train CSV, as I remember. Train.csv. Oh, yeah, we have pretty huge data set. What do we have here? Today, we will try to solve this problem using regression techniques. We have a data set of 1,400 rows, 81 columns, and we need to predict a sales price. So let's actually split this data into X, and Y. X, in our case, will be all the columns in our data set without sale price. Without sale price. X is equal 1. And Y, our target variable. Our target variable will be df of df from sale price. Sale price. Okay, in the same manner as we did with our toy data set of 15 samples, we will try to dig into this one. This is already 80 columns. We had one column, and now we have 80 columns. And Y, what is Y? Y is just a target. Okay, what first of all we need to understand that linear regression as a machine learning model can work only with numerical descriptors. And if you will have a look at a head of our data frame, it has some descriptors which is not numerical. This is a strings, pave, none, reg, and so on. So we either need to drop them, to exclude them from our training data, or we need to transform them to be a numerical one. And right now I will demonstrate you how you could do it. Then let's take a look at the feature name, info. Sorry, it's not the correct way. Some of our column is object type, some of them are integer, float, and so on. Let's do one more step of exploratory data analysis, value counts. What is wrong with value counts? Sorry. X, and then we called value counts. Something is wrong with this method. It should return number of unique values. Okay, let's try to do and unique. Okay, it's better. Right now it's better. And you see that we have many columns which has a lot of unique values, ID, loteria, and so on. Okay, today we will simply just avoid all the columns which is not a type of numerical. For this purpose, we will what should we do? The types for E in X, the types E equal if E not equal to O. Let's do like this. Yeah, right now you see I used a list comprehension syntaxes, and I picked every data type in our column, and I checked if its data type is equal to O. O is the same as object. And you see I got all the columns which has a numerical type, and there are 37 numerical columns in our data frame. Right now we need to pick up a names of this column. To do so, we will just check X columns, X for column, X column, if X from column not equal, sorry, something is wrong. For call if X column, let's check. Column for column in X column, if X from column, the type, data type not equal to object, big O. Yeah, right now I wrote a list comprehension equation which allows us to find all the names of a column which is not a strings, which has numerical type. I will call this variable numerical columns. Okay, we created numerical columns, and right now let's filter our data set and leave only numerical columns. I will do just like this. I will use the simple syntaxes for choosing columns. We filtered X. Let's display our X. Right now it's only numbers, and we'll use these numbers to fit our linear regression. As I demonstrated you previously, you have different ways to calculate coefficient in linear regression. But as I told you previously, you don't need to implement everything from scratch. Today it was just for the sake of understanding of linear regression because it's important for neural networks. But as always, linear regression is already implemented by somebody else. So to actually use linear regression, you need to import it from sklearn dot linear model import linear regression. Yeah, and this method linear regression will do all the stuff for us. It will help us to fit a linear regression model without actually implementing all this matrix multiplication. So how to do it? First of all, we need to create an instance of a method of this class, of linear regression class. Instance of linear regression. And then this LR, this variable which I created, has two important methods. First one is fit. And this fit method, if you will look inside, it takes two arguments. It takes x and y, vectors of x and y. Right now, x is a vector of a size. It has 37 columns and approximately 1400 rows. So I will fit x here, and also I will fit y here. This is all. At this stage, like 2 lines of code, we will calculate all the necessary coefficients for linear regression. We will calculate all the values of slope, and we will calculate all the values of intercept. Okay, let's do like this, and we got an error. What's going on? Here x contains NaN values. You see that linear regression that cannot work with empty values. If you will have a look at our x is NA dot sum, you see that some of the columns has NaN values. For instance, frontage, max area, and that's all. And if you're working with linear regression, it is not possible to find coefficients if you have empty values. Why it is so? Because inside this method, you need to multiply matrices. And you cannot multiply matrices if some of the value is infinite or they are missing. So what you can do here? There is 2 tactics. You can drop the rows, which has missing values. Actually 3 tactics. Drop the rows, which has missing values, and you can drop the columns, which has missing values. Third strategy, you can fill missing values with something else. You can fill them with mean, median, standard deviation, or maybe with just 0. Since today we don't go deeply into the process of machine learning, we will just fill all the missing value with 0. How to do it? We will create one more cell, x, fill NA with 0. Using this simple command, I will find all the NaN values in our data frame, and I will fill these values with 0. Okay, let's do like this. Let's check one more time if there are any missing values in our data frame. No, right now 0, 0, 0, and you should believe that all the missing values right now is not existing in our data. Okay, let me delete it. Once again, let's try to call linear regression using 37 different parameters and trying to fit it to calculate the price of our house. Delete, sorry. Okay, yeah, right now we succeeded. We were able to call linear regression, we fitted it, and you see that we have this small sign here. Okay, let's have a look at this linear regression and what method it has inside it. It had method coef. Coef is the same as a slope in our previous part of the session. Let's check it. You see coefficient, and right now you have 37 coefficient. We speak about linear regression with 1 parameter, and right now we have 37 parameters. And if we have 37 parameters, we have 37 different coefficients. Each parameter has its own coefficient, and you can see actually from this coefficient which of parameter is most important for this particular problem. Okay, and once again, we automatically calculated the best possible linear model. And once again, we can calculate intercept. Yeah, it's called the same way. You can see that intercept in this case is 484. It's just one value. So our linear regression outputted for us 37 coefficient and 1 intercept. So 38 values in total. Okay, right now let's make a prediction using linear regression. Linear regression predict x. Predict x. And it is outputted for us a big vector. Let's call it x predicted. And the size of this y predicted is the same as the size of x matrix shape, 1460. So it is tried to predict price of the house for each of the line in our data frame. Okay, we have true values of y. True values of y. Let me show you this data set, which also has the same length. So we have two vectors. We have vectors of true values, y, and we have values predicted from our linear regression. What we can do, we can measure a matrix. We can measure how good is our predictions right now. Okay. Once again, during our previous exercise, I implemented root mean square error by myself using NumPy and Python. As always, you do not need to do so in your practical life, in your practical practice of data science. You need to know where you can import it. So to import root mean square error matrix, you need to import sklearn.metrics and from sklearn.metrics import rms root. How it is called? Mean square error. Yeah, mean. You see how many metrics you have. If you go inside sklearn metrics, you see how many different metrics we have in machine learning. And today we talk only about one of them. And if you are really want to become a professional, you need to understand which metrics is the best for this particular case. But right now we're talking only about mean squared error. Yeah, like this. We import mean squared error as MSE. Okay. And already this matrix is implemented in sklearn. We can call it, and we can pass our two vectors inside it, y, pred. You see, we got a value of mean squared error, and this value is okay. Whatever, it doesn't matter. It's just some big values. So you see that to train a machine learning model, you actually need 2 lines of code. 3 lines of code. You import your machine learning model, you feed it, and that's all. You create an instance of class and you feed it. And in the same manner, you can do with neural networks. In the same manner, you can do with decision trees, gradient boosting, and so on. Machine learning right now in 2023 is really extremely simple. But there is many details which we need to understand to make it works better. Right now, this regression, we don't do any good job about it. We just did a very simple approach for calculating linear regression. And actually, it is working. Right now, we can do a prediction about house prices based on 37 parameters. One more thing. When you do some prediction, you can inspect how actually good they lie with respect to the real values. For this purpose, you should use scatter plot. And on this scatter plot, you will plot y and y predicted. plt.show and plt.x label equal to y true. And this is y predicted. Oh, sorry, I put y predicted. Yeah. You see on the both axes we have y values, but on the y-axis we have values of house prices, which is real, and on the x-axis, we have real house prices, and on y-axis we have predicted house prices. And in a perfect condition, they should lie directly one to each other. So y predicted equal to y true. Right now, it's not really so, but after all, our results is not so bad. So y true and y predicted is correlated right now. They have some positive linear correlation. At this purpose, when you do this prediction using linear model, you can check other metrics. Previously, we just spoke about mean squared error, but also it is important to know how you can use other metrics. For instance, you can measure correlation. All of you know about correlation. This is a measure of linear dependence between two variables. Right now, just without measuring, I can see that linear correlation exists here, but let's measure it. For this purpose, you need np.core coefficient, and you pass two vectors inside it. you see, yeah, let me call 0, 0, 1. Yeah, right now we measured the correlation between predicted values using linear regression and true values of linear regression of house prices. And the correlation between them is 0.9. It's extremely good correlation. So our values in a good linear correlation, and actually we may say that our model is not so bad. But on the next lecture, I will explain you what we did wrong here, because our procedure, our pipeline was not absolutely correct for this problem. Today, I will just demonstrate you how simple you can use linear regression. And on the next lecture, because we don't have enough time right now, we will speak what should you make, what steps you should actually make in your pipeline of machine learning prediction. Okay, we measured linear correlation, and another good metrics is R-square score. To use R-square score from sklearn metrics, you need to import it. R2 score. R2 score. R2 score is a value from minus infinity to 1. And when it is close to 1, you have a good model. When it is not close to 1, you have bad model. Okay, let me demonstrate you how you can calculate another metrics. Once again, you need to understand metrics is just one number which you can obtain from two vectors. One vector real values, another vector is predicted values. R2 score. R2 score, we pass y and we pass y predicted. Okay, let's see. R2 score is 0.81. Actually, just from my practical point of view, this is a good R2 score. Our model is pretty well, and R2 score is another metrics which sometimes you should choose. So to sum up for today's lecture, I just ran out of time. I'm sorry for this. Today we discussed about one of the most important algorithms in machine learning. On the next lecture, we'll discuss another really important algorithm, which is decision trees. But right now, we discussed only about linear regression. Why it is important? Because sometimes you can solve many machine learning problems in real work using linear regression. And also, linear regression is a small part of neural network. Each neuron in neural network is a linear regression, actually. So you need to understand it in a simple words. Today, we discussed what is the slope, what is the intercept, how you can change it, and how your line is changing with it. Then we demonstrated how you can do linear regression with one parameter, and how you can create a line which is in a good feed for your points. So we tested different random lines. We measured the performance of each line right here using RMSE. And then we understand that finding a best line, we should use this equation after all. And using this equation, we were able to find a line which has mean squared error of 29, which is much lower than our previous attempts. Okay, then we tested a second approach. And also we have a question in chat. Yeah, these two approaches, you can mathematically prove that they are equal. So this formula and this formula is just two different representation of the same, how to say, of the same method. So this formula is just much more convenient when you are moving from the one-dimensional case to many-dimensional case, like in our last exercise, when we have 37 features. So this matrix is applicable for this case. And this approach with formulas is not applicable. Okay, and using this approach, it is possible to find the best line. You see, by the way, that values of slope and intercept using these two approaches is the same. So actually, this is the same kind of ways to find these two values. Okay, and then I demonstrated you really briefly, sorry for that, we just need to finish, that downloading simple data, we can run a linear regression in several lines of code. First of all, you need to exclude all the values which is not numerical, or you need to transform numerical variables inside to numerical ones. And then you need to avoid infinite or non-existing numbers. If you have some nuns in your dataset, you should drop them. And you have 3 strategies to drop them: drop rows, drop columns, or fill them with zeros. And here we used a simple method. We just filled all the non values with zeros. Then we called linear regression in 2 lines of code, very simple. And also, it is important, sometimes you should inspect coefficients of your regression. Since we have 37 features, we have 37 coefficients. And we have one more coefficient for intercept. So in total, 38. We predicted y using our new line, and then we measure performance of our model. You can do it in many different ways. I will demonstrate it you on the next lecture. But here we just plotted predicted values with the true ones, and then we measure correlation and R2 score. Okay, this is all for today. Hope you got understanding of linear regression. Next time, I think we don't move to neural networks yet. We should deeply dive into the procedure and the pipeline of machine learning. So I think we will extend our course for 1 or 2 more lectures, just because we are not moving as fast as I expected. But it's not a problem. I like to do it. Okay, guys. Next lecture, I think it will take place on Saturday. So please be ready. And on Saturday, I hope we will, first of all, discuss about the procedure of validation, because as I told you, today we did it not in the right way. We just made a toy example of linear regression on real data. We will discuss about validation procedure, and we will discuss about one more new model, which is decision tree, which is also really important. And right now, many state-of-the-art machine learning models is based on a decision trees. Okay, guys, thank you for your attention, and hope to see you next time. Thank you, guys. Bye-bye. Oh, sorry. Any questions? Any questions? Reminder. Okay, thank you. Okay, I will stop recording, and